Hello. So this week we are going to continue with our revision of the AC theory, outcome 8. As last week, I want you to pause the video and make sure you've got all your notes that you were given while you were at college, a pen and a piece of paper. So just pause it and come back and press play again when you've got all that together. Right, so this week we are going to look at capacitors and their characteristics and corresponding equations. We're going to do some calculations involving the capacitive reactance. We're going to learn how to calculate the impedance of a combined resistive and capacitive circuit. And we're going to look at doing that mathematically and using a phasor diagram. I hope you'll remember that means a triangle. And we're going to have a quick look at power factor again. I'm going to cover that in more detail in the week after half term. Okay, so first of all, we're going to do a quick recap of points from last week. We were looking at inductors and resistors. And if you remember that resistors are unique in that the same equations as DC apply when they are in an AC circuit. The opposition to the current is still the resistance. It's just the resistance in ohms, the same as if it was in a DC circuit. And the phase angle between the voltage and the current is 0 because the voltage and the current peak at the same time. There is no lag between them. Now, inductors are different. They do react to AC. Just remember, inductor is just a fancy name for a coil. Because they do react to AC, they have what we call inductive reactance, and that is the opposition to the current in an AC circuit, and it's denoted by this letter XL. The equation that we use to calculate the reactance is this one here, 2 pi FL, where L is the inductance in henries and XL is the reactance, the inductive reactance, and that's in ohms. Now, in this case, with an inductor, there is a phase angle. There is a difference between the voltage and the current peaks, and they are 90 degrees out of phase, and the current lags the voltage in an inductor. Because if you remember, the inductor doesn't want those electrons. It's resisting that current flow, and so the voltage peaks before the current finally starts to flow through it. Now, quite a few of you are confused with the letter for impedance, Z. Don't get the impedance and the inductance mixed up. It's a common mistake. So impedance is our Z, and that is the total opposition to the current flow in an AC circuit. Okay, so it's the combined resistance and opposition from all of the components. And where you have an inductor and a resistor in the circuit, we use this formula here, okay, to calculate the total opposition to the current flow. Okay, so that's what we covered last week. So moving on this week, we are looking at capacitors. Again, these are a reactive component, and we use the letter C to denote the capacitance, okay, and that is measured in farads, denoted by the letter F. If you can't remember how a capacitor works, please revisit this engineering mindset clip on YouTube. It's excellent, and it's a really good explanation of a capacitor, and you can just remind yourselves of how it works. Okay, so here we have our phasor diagram showing our voltage peaks and our current peaks, and you can immediately see that these are out of phase by 90 degrees again, but it's different to our inductor, okay, because we've got our current leading our voltage by 90 degrees, because a capacitor really wants those electrons, the inductor doesn't, okay, the inductor doesn't like them. So this is how we draw our phase diagram for a capacitor. with the current still on the same line, but this time we draw our voltage going down. And the resistance to the current flow, the reactance, still the reactance, but the symbol is an X as before, but this time it's got a C next to it. I'm sorry, that's right up against that picture. Hopefully you can see that clearly. Here we go, key equation to memorise. Capacitive reactance is equal to 1 divided by 2 times pi times F, which is our frequency, times C, which is our capacitance, which is measured in farads. Okay, so we're going to go straight into a question. An 8.7 microfarad capacitor is connected across an AC supply. Calculate the capacitive reactance if the frequency is 60 Hertz. Now you can see I've got that there. That should be on an animation. Sorry about that. The first step is to identify the equation, which is the one I had on the previous slide to memorise. The second step is to identify each letter in the equation. Here, the 8.7 microfarads is our C, and the 60 Hertz is our F. Now we rewrite the equation with the numbers in the correct place, and that's what we've got here. Okay, we've got our 1 divided by our 2 times pi times our frequency, which is 60 from the question up here, times our capacitance. Now this 10 to the minus 6, that is micro, okay, that is microfarads. Milli was times 10 to the minus 3, micro is times 10 to the minus 6, and that simply means we bounce our decimal point 6 places to the left, and that gives us this number here. Okay, so if you put all that into your calculator, you get a capacitive reactance of 304.9 ohms. Okay, so we're going to look at another question. We've got a capacitor. This time it's 0.1 microfarads, and the frequency of our supply there is 15 kilohertz. So again, look out for those prefixes. Okay, you've got kilo and micro here. Step 1, identify the equation. There we go, same equation again for our capacitive reactance. Step 2, identify each letter from the equation. So we've got our capacitance was 0.1 microfarads times 10 to the minus 6, which is the same as this number. Okay, that's what that means. And our frequency is 15 kilohertz. Kilo is 10 to the 3, and so that's equivalent to that number there. Okay, so we rewrite our equation with all of the numbers in the correct places. 2 times pi times our frequency times our capacitance, and that gives us 106 ohms of reactance. Okay, capacitive reactance, that's how much that capacitor resists the flow in an AC circuit. So now I want you to look at this circuit here, and I want you to calculate the capacitive reactance of this particular circuit. So do that, pause the video, and then when you're ready with an answer, press play, and the answer is on the next slide. Okay, here's your answer, 318.31 ohms. I hope you got that. If you didn't, please go back and try again. Make sure you converted the microfarads correctly and have another go. So now, again, I want you to pause the video and do this little quiz. It's a quick one, just to check you're retaining this information. Okay, I hope you got most of the questions right on that quizzes check. And now we're going to move on to impedance again. As I say, there was a lot of confusion on the assessment worksheets last week, and so I just want to do another recap this week, this time obviously looking at capacitors in conjunction with a resistor. So as a reminder, impedance is our Z, okay, it's the letter Z, and it's measured in ohms. And it's a combination of the resistance and the reactance of a circuit. So it's the total opposition to the current. There's our triangle with our phase angle in place. And as before, just use Pythagoras to work out the missing figures. And we've got phi is our phase angle or phase shift. So for a resistor and a capacitor, the impedance triangle is drawn like this. If you remember, for an inductor, the XL, our inductive reactance, went upwards from our resistance, but with a capacitor it comes down. You've had an explanation as to why that's the case. I want you to look through your notes and make sure you understand why. The phase angle always comes between the resistance and the impedance. Okay, so using these equations, we can find any of our missing figures. And this equation is exactly the same as for an inductor. Our cos phi is our adjacent over our hypotenuse, which when you look at your triangle, your adjacent is still your r and your hypotenuse is still your z. So it's still r over z. So it's exactly the same equation as for an inductor. Okay, so now we're going to do a two-step example. And this time we've got a circuit supplied at 230 volts and 50 hertz, and it consists of a resistor of 500 ohms and a capacitor with reactance of 210 ohms connected in series. So first of all, it wants us to calculate the impedance of the circuit. Okay, so straight away you should be thinking, that's my Z. All right, so identify the equation. Look at your numbers in your question and identify the letters from the equation. Rewrite the equation and rearrange it if necessary. So, step 1, which equation do we want? We want our Z. R squared plus XC squared and all of that square rooted. Where are the values for this equation? Z is what we want to find. R is our 500 ohms. And our capacitive reactance, our XC, is 210 ohms. Now we insert these values for each of the symbols in our equation. There we go, 500 squared is our resistance squared, plus 210 squared, which is our XC squared, and it's all that lot square root. And that gives us an answer of 542.3 ohms of impedance, Z impedance, okay? So that's how much the resistor and the capacitor in series will resist the flow of electrons. Now the second part of the question was asking for the phase angle, okay? So that's our letter phi, and here's our equation. Cos phi is our R over Z, resistance over impedance. Now, impedance was the figure we just calculated, this one here, and our resistance, 500 ohms, was in our question. So we insert those figures into our equation, 500 over 542.3. And we just do that straightforward division at the minute, and that gives us 0.92 leading. And it's leading because the current is leading the voltage. So this is the power factor, and this is giving us the relationship between resistance and impedance, but it's not told us what the angle is. It's just given us this relationship, this power factor, okay? So in order to get the angle, we must use our shift button on our calculator and cos to give us cos to the -1 of the number up here, 0.92, and that's going to give us an angle, a phase angle of 23 degrees leading. Okay, run through this yourselves with your calculator and please make sure you get the same answers that I did. Okay, so finally, the answer to that question, we've calculated the impedance of 542.3 ohms and the phase angle of 23 degrees leading. If you were asked to draw the impedance triangle, it would look like this, and you would label each of the sides with the values that you've calculated. Alternatively, it may ask you to draw the triangle to scale and then measure the impedance. So that's something we're going to have to cover when we're back in college. But you would work out a suitable scale for the ohms, and then you would measure this line here, and it would tell you, and then using your scale, you'd be able to work out what the actual value for the impedance was. And you'd have to have a protractor to measure this actual angle here. Given the choice, I would definitely go with the mathematical option. I think that's more straightforward and less room for error. However, I just need to cover this off just in case they ask you to draw it to scale and then measure it. But we will cover that when we're actually in college. Right, so what have we covered today? We have looked at how to calculate our inductive reactance. That was from last week. That's a key equation. All of these you need to remember. Today we covered capacitive reactance. Similar equation, but a 1 over. Our impedance is our resistance squared plus our reactance squared. Phi is the phase angle, same as ever. The power factor is cos phi. It's this relationship of resistance divided by impedance. An impedance triangle for an inductor looks like that, with the reactance going up from the resistance. And our impedance triangle for a capacitor sort of is the mirror image of it and goes down like that, with our XC going down. Okay, I hope that's reminded you all of these key things about capacitors and inductors. And now I would like you to complete the assessment, the worksheet here online as normal. And I hope you get on all right with it. Please don't hesitate to call me or email me if you have any questions at all. I'm here. I can answer your questions. Okay, so good luck for that. And I'll see you all after half term.